Hello and welcome to the class on testing of hypotheses. The statistical theory can be categorized as descriptive statistics and inferential statistics. In case of descriptive statistics, we describe a dataset with the help of diagrams or numerical measures, whereas in case of inferential statistics, it deals with drawing conclusions about a population using the information which is obtained from a representative sample. Inferential statistics includes estimation of population parameter from the sample statistic or hypothesis testing, where we examine a hypothesis. A statistical hypothesis is some statement about a population which we want to verify on the basis of information available from a sample. We are very well familiar with the terminologies population parameter and sample statistic. We can make the statement such as population mean is equal to the sample mean, population variance is equal to the sample variance, or the statements can take the shape such as mu is equal to x bar, sigma square is equal to v, mu is less than x bar, sigma square is equal to v, mu is greater than x bar, sigma square is equal to v, mu is equal to x bar, sigma square is less than v, mu is equal to x bar, sigma square is greater than v, or mu is less than x bar, sigma square is greater than v. If the statistical hypothesis specifies the population parameter completely, then it is termed as a simple statistical hypothesis. For example, in the given statement, we state that mu is equal to x bar and sigma square is equal to v. Here we have specified a fixed value of sample mean x bar and a fixed value of sample variance v for the population parameters. These fixed values of sample statistic will be tested against the population parameters. The population parameters are tested against a single value of sample statistic. If the statistical hypothesis do not specify the population parameter completely, then it is termed as a composite statistical hypothesis. For example, if we look at all the given statements, we observe that we are testing the population parameter against more than one value of sample statistic. Test of a statistical hypothesis is a two-way action after the experimental sample values have been obtained. The two actions being either acceptance of the hypothesis or rejection of the hypothesis. We can make the statement about the sample and the population such as mu is greater than x bar or mu is less than x bar. But these two statements are biased. They reflect a preferential attitude to one or the other sample or the population. Now, if we say that population mean is equal to the sample mean, this statement denotes a hypothesis of no difference. It suggests a neutral or null attitude regarding the outcome of the test. This is called as null hypothesis, which is denoted by H0. That is, mu is equal to x bar, that is, mu minus x bar is equal to 0. Null hypothesis is tested against an opposite hypothesis known as alternate hypothesis, which is denoted by H1. If null hypothesis is mu is equal to x bar, then the alternate hypothesis can be mu is greater than x bar, or mu is less than x bar, or mu is not equal to x bar. Mu is greater than x bar or mu is less than x bar are tested in one-tailed test, whereas mu is not equal to x bar is tested in two-tailed test. Now, if we are rejecting null hypothesis when alternate hypothesis is false, we are committing a type 1 error. The probability of type 1 error is alpha. Alpha is the probability of rejecting null hypothesis when null hypothesis is true. And if we are accepting null hypothesis when alternate hypothesis is true, we are committing a type 2 error. The probability of type 2 error is beta. Beta is the probability of accepting null hypothesis when null hypothesis is false. Type 1 error is considered as more serious than type 2 error. If we draw a sample from a population and compare the means, we observe that the value of sample mean is not exactly same as that of the population mean. The sample mean is different from the population mean. X bar will not be exactly equal to the mu. The difference between X bar and mu may be because of the errors of sampling, or the difference may be because the parent population is different from the population under consideration. If X bar and mu are different due to errors of sampling, then it will have some limiting value, let us say delta. If the difference between X bar and mu is less than delta, we say that the difference is because of sampling errors. And if the difference between X bar and mu is equal to or greater than delta, we say that difference between X bar and mu is significant. Now, the statistical procedure for deciding whether the difference under study is significant or non-significant is known as test of significance. The null hypothesis will be rejected if the difference between sample mean and population mean is equal to or greater than delta. All the values beyond mu plus or minus delta form a region which is known as critical region or region of rejection. The values within mu plus or minus delta forms a region of acceptance. The probability of type 1 error is known as the level of significance. It is also known as the size of the critical region. The probability of type 1 error is alpha. Alpha is the probability of rejecting null hypothesis when null hypothesis is true. An ideal test of significance would be the one which properly keeps both types of errors under control. In case of test of significance of the difference between the sample mean and the population mean, we have to determine with reasonable degree of confidence the range within which the true mean lies. The limits of this range are referred as confidence limits, and the range between these limits as confidence interval. The probability of type 2 error is beta. The beta is the probability of accepting null hypothesis when null hypothesis is false. 1 minus beta is called as the power function of the test hypothesis against the alternate hypothesis. The value of power function at a parameter point is called the power of the test at that point. In any test, the critical region is represented by a portion of the area under curve of the sampling distribution of the test statistics. A test of any statistical hypothesis where alternate hypothesis is one-tailed, that is right-tailed or left-tailed, is known as one-tailed test. For example, if null hypothesis is mu is equal to X bar, alternate hypothesis in right-tailed test will be mu is greater than X bar, and alternate hypothesis for left-tailed test will be mu is less than X bar. In right-tailed test, the critical region lies entirely in the right tail of the sampling distribution of sample means. Whereas in case of left-tail test, the critical region lies entirely in the left tail of the sampling distribution of sample mean. Whereas a test of statistical hypothesis where null hypothesis is two-tailed, that is, mu is not equal to x bar. It means mu is either greater than x bar or mu is less than x bar is known as two-tailed test, and in such case the critical region lies in both the tails of sampling distribution of sample means. We studied that the total area under curve in normal distribution is equal to 1. The given diagram represents sampling distribution of the means with mean mu and variance sigma square. Here, the level of significance alpha is 5% and delta is 1.96 into standard error. In this image, critical region is shown by shaded area. Mu plus or minus delta denotes the region of acceptance. In two-tailed test, critical region lies in both the tails. In case of right-tailed test, the critical region lies entirely in the right tail, whereas in case of left-tailed test, the critical region lies entirely in the left tail. P-value. From the given data, we calculate the value of a test statistic, say Z value, P value, F value, or chi-square value. Attached to each value of a test statistics is a probability, that is p-value. P-value describes the chance of getting the observed effect if the null hypothesis is true. If the p-value is very small, less than 0.05, then it is unlikely that we could have obtained the observed results if the null hypothesis were true. So, we reject the null hypothesis. We get enough evidence to reject the null hypothesis. We say that the results of the test is statistically significant. And if the p-value is very large, it is more than 0.05, then there is a high chance that we could have obtained the observed results if the null hypothesis were true. And we do not reject null hypothesis. We do not have enough evidence to reject the null hypothesis. We say that the results of the test is statistically non-significant. Thank you.